thank you very much for inviting me and on behalf of SNC Lavilin to share with you our experience in engineering and building the SaskPower Boundary Dam Carbon Capture Project. It's a project that's dear to me personally. I've been personally involved in projects for the last 5 years, starting with the front-end engineering design in 2009, which we conducted in partnership with our carbon capture technology provider, which is Shell Cansol, represented here today with Devon Shaw. So we completed the FEED in 2009, which led to the engineering, procurement, construction contract to be awarded to SNC Lavilin in 2010. We started construction in May of 2011, and we finished the construction. The plant is mechanically complete. We've just started the commissioning, and we are on track to be operational. The target is for the second quarter of this year. We have in this project an excellent client, a client in the name of SaskPower, who's shown great leadership in the world of carbon capture, and great leadership in taking the bold step to build this project, which will be, when it comes online later on this year, the largest post-combustion carbon capture project in the world. Others will be built subsequently, but that is the case for now. So that took a lot of analysis on the part of SaskPower, but a lot of leadership as well. So here's what I propose to do for you today. I'll give you, if you'll allow me, a brief outline on who SNC Lavilin is. I'll give you a briefing on the Boundary Dam Carbon Capture Project. And also I put a few slides together highlighting the challenges that we faced, if you want, in this project. When we started the project, our goal, obviously, as an EPC contractor, is to deliver a quality project, deliver it on budget, and deliver it on schedule. This is a large scale-up exercise, if you want. We did encounter some challenges, some we had planned for and put measures in place, others just came about due to the nature of the project. So in those slides, I'll brief you and highlight some of the interesting points. And I'll conclude by giving you a breakdown at a high level of the project cost and some considerations with respect to key factors that would impact the cost of the project if it were to be built again, either on the same site or on other locations. So SNC Lavilin, who are we? We're a global engineering, procurement, and construction firm. We have some 34,000 employees worldwide. We have permanent offices in 40 countries, projects in over 100 countries. We were founded in 1911, so we're very proud that a couple of years ago, having celebrated our 100th year of being in business, and we are a publicly traded company. Our main areas of expertise, of interest, if you want, is power generation, including transmission and distribution, the oil and gas field, including chemical plants, mining and metallurgy, infrastructure, environment. We do operate and maintain plants on behalf of clients, and we do have a segment of the company that will facilitate project financing for clients if so desired. As you'll see, carbon capture, at the heart of it, is our large chemical plants. So in our division, which is the oil and gas division, this is an ideal fit for us to implement these types of projects. They are implemented in conjunction with power plants, so if there's an integration aspect of the project that's required, our power division gets involved so we can offer the complete package. We can take the project from cradle to grave. We'll take the project through studies, analyze various technologies, come up with the optimum approach for a project, We can take it to front-end engineering design and the full implementation through engineering, procurement, construction contracts, either EPC or EPCM. We do offer operator training, commissioning and startup, and as I said, offer flight operation and maintenance if required. So the Boundary Dam Carbon Capture Project. A little bit of background about Boundary Dam itself. It's located in Estevan, Saskatchewan, obviously owned by SaskPower, who's the provincial power utility. It is a 800 megawatt nominal coal-fired power station, firing lignite coal, which is literally dug out of the ground a few hundred yards away and brought to the power plant. It has 6 units installed from 1959 to 1978. 2 units rated at 60 megawatts, one being shut down recently. 3 units rated at 150 megawatts, and last unit rated at 250 megawatts. So what are the drivers for carbon capture for SaskPower? One of the main factors is that we have new federal regulations for coal-fired power generation that are effective 2015, mandating that new plants or plants that have reached the end of their lives and will be retrofitted must meet a CO2 emission cap of no more than 420 kilograms per megawatt hour, which is about 1,000 pounds per megawatt hour. This can only be achieved by implementing some form of carbon capture. Coal-based power generation is an important part of SaskPower's portfolio. There's a large local coal reserve, which offers price stability as far as the utility is concerned. There's a possibility for a CO2 enhanced oil recovery adjacent to the power plant. The Weyburn oil field is only a few kilometers away and has already been doing CO2 enhanced oil recovery for the last 10 years with CO2 that is purchased from North Dakota. At the front of this project, SaskPower did conduct a study. Boundary Dam is at the end of its useful life. A decision had to be made whether to retrofit it and implement carbon capture, or look at the best alternative, or next best alternative, if you want, which would have been gas-fired combined cycle. Their analysis at the time showed that over a 30-year lifespan, with the assumptions made that either alternative would have about the same impact to the ratepayers. But SaskPower liked the stability and predictability in price that coal brought to their portfolio, so chose to go ahead and implement retrofitting one of the units at Boundary Dam and including carbon capture. So the project entails refurbishing completely unit number 3, which is rated at 150 megawatts. That means installing as well a new steam turbine generator set with steam extraction at a pressure suitable for regenerating the amine in the carbon capture plant, installing new controls, installing new emissions control, and installing what I call the carbon capture system. So SNC Lavilin's scope for us is this portion of the project, which is the carbon capture plant here, the CO2 compression system, and in the background you see here cooling towers and pumping station, which form what we call the heat rejection system with the underground pipeline. You see the connecting duct here going to unit number 3, which is just adjacent to this stand. Our scope of service was to do the front-end engineering design, and as I said earlier, the engineering, procurement, and construction in a fully integrated EPC contract fashion. And that was a very important aspect for SaskPower in selecting our offering, if you want to go ahead. Our technology partner, CanSolve, is a subcontractor to us, if you want. They provide the CO2 and SO2 carbon capture technology, which includes the amine and key design and process design parameters. And the process guarantees are offered to SaskPower as a flow through to SNC Lavilin. We also provided operator training to SaskPower and are providing assistance in the startup and commissioning. SaskPower itself is actually conducting the startup and the commissioning. And SaskPower is also conducting the refurbishing of the boiler itself and installing the new steam turbine. So the status, I've covered a little bit of that. The FEED was done in 2009. We started detail engineering in February 2010. Construction was started in May 2011. Mechanical completion, which is where we handed over the project to SaskPower, was completed in December of this year. Commissioning and startup is on the way as we speak. The power plant upgrade, which is spearheaded by SaskPower, the completion target is the first quarter of this year. And as I said, the start of operation for the whole facility is the second quarter of this year. So a few highlights as related to the engineering and construction. I'll just give a very, very high-level description of the process, and I'll leave Devin from CANSOLV to get into the details this afternoon. But essentially, we take the flue gas from the unit number 3, and through 2 separate amine processes, we first capture all of the SO2 in the front end of the process, we capture then the CO2 in the back end of the process. The system is designed to capture 3,300 metric tons per day of CO2, which is about 1.2 million tons per year, which is about 90% of the CO2 level in the flue gas. The CO2 is compressed to 2,500 psi and sent via a new pipeline to the Weyburn oil field and is used for enhanced oil recovery. And the SO2 is converted into sulfuric acid. So this amine process, in the back end, you get the pure product, which is SO2. And in this case, we convert it through a small acid plant that we've provided as part of the carbon capture plant into sulfuric acid. That feature of removing the SO2 in this fashion was deemed quite attractive to SaskPower when they were evaluating the various options. SO2 must be removed, otherwise it would bind with the CO2 amine and make a permanent salt. So the option would have been to scrub the SO2 in a conventional fashion using limestone scrubbers. In this case, limestone is not native to Saskatchewan, so it becomes a cost. And the product that you make is calcium sulfate, and it would have been heavily contaminated with various metals in the coal, including mercury, and would have been deemed a hazardous product, so you end up with a product that you have to pay to landfill. Using this approach, you end up with a product that you can sell, so you do not have that double cash flow stream, if you want, negative cash flow stream. So that was quite attractive. These 2 processes are exothermic, so there's a lot of cooling required. We built a large cooling system, which I showed in the picture earlier. So these are the main components. Very briefly, in the carbon capture plant, you see here the flue gas coming in. We have 2 absorbers in series, one removing the SO2 and the other one the CO2. I'm showing you this so that when we get to the equipment, it makes sense to you. And then the so-called rich amine from these absorption processes are sent to 2 separate strippers, where steam from the power plant is sent to reverse the chemical reaction. So we get pure CO2 in the CO2 stripper, we get pure SO2 and the from the SO2 stripper, which is sent to our small sulfuric acid plant. And then we produce about 60 tons per day of sulfuric acid, which will be sold in the local market and likely used to make fertilizer. So some descriptive words on the plant itself. The carbon capture plant is here. It's about 420 feet long, 120 feet wide, 75 feet high at the tall end, 30 feet high here. The front here is the carbon capture building, the carbon dioxide compressor building. You see here the two absorbers. I have a couple more pictures of this. We have about 156 pieces of equipment. Some of those are some of the largest commercially available equipment that you can buy in the marketplace, including these plated frame heat exchangers. If you were put a human being would stand about here. So we have quite a few of these, and literally we had to push the boundary and buy the largest that was commercially available. One novel aspect that we took to engineering is use concrete absorber construction. Typically these would have been built out of steel, but using the concrete construction approach, these absorbers have their multitude of absorption sections, if you want, and Devin will get into those details. But typically this would have been built of steel. We used this approach for two reasons. It significantly lowered the cost, which we were able to pass on to SaskPower, but also prevented to build large steel vessels in the field, which is a bit problematic in this location. So the construction, if you want, is concrete block, ceramic tile lined with additional lime material where it's flooded. And it results in a fairly compact footprint because we have absorbers that share a wall. They're square. And as I said, the main consideration was for cost reasons as well. Another key vessel is the so-called CO2 rich-amine stripper. Very much in line with the vessel that was shown earlier. This vessel was built off-site. Again, one of the strategies that we used in building this project is to take as much as possible of the construction off-site, whether it's using modular construction approach or taking a vessel that could have been built on site, but we opted to build it in a shop. And one of the main reasons is labor in Saskatchewan it's a very competitive market, and we want to decongest the construction site and reduce the amount of labor to the optimum level that we will use in the field. So shop construction enables us to use shop labor. We can manage the construction in the shop much better. And as I'll show later as well, one of the challenges in Saskatchewan is the weather. You plan, you have a schedule, but then the weather happens. And having material construction in a shop helps you stay on schedule. So this was a very heavy load. The piece of equipment weighs 240 tons. It took a number of days to bring to site. Very much like was described earlier, we had to review the suitability of construction of certain bridges. Power lines had to be lifted, some of them permanently, but in the end it was worth it. Another important piece of equipment is the CO2 compressor. It was procured by SaskPower and free issued to us. It's a 20,000 horsepower motor, and as I said, produces CO2 at 2,500 psi. Here's the heat rejection system. It has a cooling capacity of 680 million BTUs an hour. It rejects all the heat generated both by the chemical reactions that are within the facility, as well as the heat generated by the CO2 compressor. It also includes a significant water treatment plant because we also try to minimize the amount of water that is sent to the lagoons. So some of the water that's actually recuperated in the flue gas cooler is actually sent here and we treat it. A few construction highlights. We started construction in May 2011. At peak, we had about 600 trades. Health and safety is important both to SaskPower and SNC Lavilin. And to date, we achieved 4 million man-hours worked without a lost time incident. This is for our portion of the project as well as SaskPower. One of the challenges is weather extremes. In the summer, it gets up to 107 degrees Fahrenheit in Saskatchewan, and in the winter, we experience minus 50 degrees Fahrenheit. One of the key factors is closing the building on time. We had planned to close the building initially in December of 2011. We missed that, and that caused a domino effect on labor. That's where this modular construction approach came in to help us. We use modular construction where we could. We have 12 what we call utility racks, and on those utility racks we mounted large bore piping, electrical trays, and assembled this off-site. And when they came outside, the structure of the rack formed part of the structure of the building, and you can see here all the racks being assembled. By the time we were done and the racks were installed, we had 30% of the large bore piping installed. So that came in to help us in catching up where we slipped on schedule for other reasons. Costs. The project was initially estimated by SaskPower to be a $1.2 billion project, and these are Canadian dollars. They did receive a grant of $250 million from the federal government, and the approximate breakdown is the carbon capture system is about half of this, and then the retrofit is another half. The current estimate is that the project will cost $1.38 billion. The power island upgrade and refurbishing had some surprises, so the cost went up, but we're pleased to report that the carbon capture system portion was slightly under budget. So look, what I'll do is I'll leave it at this. I had a couple more slides, and we can cover that if they're given to the audience.